Let's find the centroid of the solid upper hemisphere of radius 1. To find the centroid of a solid, first you need to know what the volume is. And of course, for many regions, you'd have to just do a triple integral to find that out. But in this case, since we have a solid upper hemisphere, we know that the volume is just 1/2 of the volume of a sphere. So 1/2 of 4/3 pi r cubed. And so in this case, just 2 pi over 3. Now the centroid is this point x bar, y bar, z bar. And by symmetry, if you have a solid upper hemisphere, x bar and y bar are both going to be 0. Basically because the z-axis is an axis of rotational symmetry. So the centroid, which is just the center of mass considering the density to be constant, the centroid has to then lie on that axis of symmetry. So it remains to find z bar. And the general formula for z bar is to find 1 divided by the volume of the triple integral of z on that region. So I need to describe the region in terms of rho and phi and theta. For rho, since it's a solid upper hemisphere, it's not hollowed out in any way, then rho starts at 0, and it extends all the way to radius 1. Since I want the solid upper hemisphere, by which we mean the positive z part, remember that means that you want to go from the North Pole down to the equator. The North Pole consists of phi equals 0, and the equator is phi equals pi over 2. And it is important you actually get this right here. You can't just take any old half of a sphere. In this case, for example, if you took the bottom half accidentally, or if you change the theta values instead of the phi values, then you'll end up getting the wrong value for z bar. For theta, we have the whole range from 0 to 2 pi, because I haven't restricted anything around the z-axis. I have the sphere all the way around the z-axis. Okay, so I have 1 over v. I have to convert z into spherical coordinates, and z is rho times cosine of phi. And then remember, I have this extra factor of rho squared sine phi before I have my d rho, d phi, d theta. So if I have rho on the inside, then those go from 0 to 1. Then phi was 0 to pi over 2, and then theta was 0 to 2 pi. Okay, so let's keep going. Let's see. For the inside integral, well, all this together is rho cubed times some non-rho stuff. And when I integrate that with respect to rho, you'll get rho to the 4th over 4 times cosine phi sine phi. And so that ends up giving you just 1/4 cosine phi sine phi. All right, so that was the inside integral. Now you have the integral from 0 to pi over 2 of 1/4 cosine phi sine phi d phi. And there are a couple ways you can do this. Some people like to use a trig identity to rewrite cosine phi sine phi using the double angle formula. Or you can just do a substitution where you say, well, if I take u to be sine of phi, then du is cosine phi d phi. And so that would make this then the integral of 1/4 of u du, which will be 1/8 of u squared. So you get 1/8 of sine squared phi from 0 to pi over 2. And that's just 1/8. Okay, so that takes care now of the second integral. So where I am now is I have 1 over v times the integral from 0 to 2 pi of 1/8 d theta. So I just get 1/8 of theta from 0 to 2 pi. So 1 over v times 2 pi over 8. And now we just have to simplify things. V was 2 pi over 3. So 1 over v is 3 over 2 pi. And the 2 pi's end up canceling, and you get that z bar is 3/8. And so in the end, we found that the centroid is the point 0, 0, 3/8. And as usual, it's worth doing a quick sanity check on this. We have a full upper hemisphere of radius 1. And well, when you have a hemisphere, it's kind of top heavy, right? Sorry, bottom heavy rather. Right, you have more of the mass kind of below the halfway point than above. And so I expect the centroid to lie somewhere below 1/2. And evidently it's not too much below 1/2. Okay, so there you go. That's how you do a triple integral in spherical coordinates.